Hello, I'm Cnix. In this video, I'll talk about the digital twin of Cnix Pascal2. A digital twin that runs inference using only CPU. Let's take a look. First, there are two things that the Pascal2-Digital Twin does not use: a database and a GPU. That's right, it means an ordinary PC is sufficient. The Pascal2-Digital Twin is based on data-driven machine learning. It learns not only physical models but also various mechanical and electrical environments that traditional physics models cannot handle. The Pascal2-Digital Twin can virtualize your real site more closely than ever before. Now, let's watch the demo.
All right. From now on, I will demonstrate the Pascal2-Digital Twin. First, let's start the digital twin. All the background processors required to operate the digital twin are now running. Next, if you look at instance 1, the engine is running. And this section represents the actual PLC I/O. First, to operate the digital twin, we need to train it. In training mode, we need to link it with the desired PVs and the desired tags. All you have to do is go into Pascal 2 and upload the pre-saved PV tag list from the config directory. When you run the training in training mode, it starts training like this. As you can see, because it trains the actual PLC I/O data online, there is no need for a separate database. Since it learns the field data online, it captures and learns the mechanical and electrical environments of the actual site exactly as they are. Due to time constraints, I will stop it here. I have a model that I previously trained, so I will load that one again. Similarly, I'll upload the I/O list. The trained model is right here. Next, once we start it within the digital twin model, it begins operating as a digital model. The difference between training and the digital twin is that the digital twin takes actual inputs in real time and infers the output. As you can see, you can check how well it infers by looking at the confidence level. You can also plot the data to compare them. For example, let's take a look at the do data. The inferred data for the do data. This part is where it makes inferences based on what it has learned. Let's zoom in on this section a bit. If we zoom in, you can see that the patterns are visually identical. It takes actual inputs and the output of the inference model follows almost the exact same pattern as the actual output. Let's zoom in a little further. If we zoom in a bit more, it shows up like this. The red line is the actual output, and the green line is the inferred output. If you look at the time gap, 832 milliseconds and then 846 milliseconds. This delay, or latency, is the time it takes to read the PLC input, perform the inference, and generate the output. It's about 15 milliseconds. This is extremely high speed. Now let's take a look at the I/O output. This is the section that just started, the inferred output for the I/O output. The inferred output for this I/O output looks like this. The blue line is the inferred output. If you look at this part, I will zoom in. As you can see, the patterns are identical. This means the training went well. The output is also generating properly. Let's zoom in on this section a bit. Like this, you can see the blue inferred output closely following the red actual output. Similarly, if we check the latency for this one as well, 637 651, staying well under about 15 milliseconds. The inferred output is tracking the actual output. Above all, if you look at the values. Looking closely here, 108, 108, and here, 109, 109. The actual output values and the inferred output values are almost identical. 101, 101, 122, 122. And the patterns are moving along identically as well. It successfully generates an inferred output that is nearly identical to the actual output from the field. This is a digital twin that allows for a much more perfect simulation of the actual field environment.